Let's take a look at question number 6 of the RACE-0 of the Secureum Bootcamp. So in this question we again have a little snippet, but it's a little bit more exciting because we actually have to look for security issues here. And we have multiple issues to select from, which are possibly in here. The first one is reentrancy. And looking at what we have a contract, which is a test contract. We are to assume that other required functionality is correctly implemented, so there's actually probably much more stuff going on here. But we only have a function called withdraw, and like you would expect from a withdraw function, we have an amount that we can withdraw, and it is external. But most importantly, it also has a non-reentrant modifier. And it gets this non-reentrant modifier from the Open Zeppelin contracts library, the Reentrancy Guard. So this should already tell us that if under the assumption that the non-reentrant modifier is always applied, meaning to all the other functions as well, and to this function we have here, there probably is not a reentrancy risk here. There's only a little problem with this code because the contract test would need to extend the reentrancy guard for this to work. But this was a little error that was made in this quiz. This is actually not intentional, and we should just assume that it actually correctly extends the reentrancy guard and that indeed all of the functions in here have correctly applied this non-reentrant modifier. But let's say we have actually a contract, a malicious contract that tries to exploit a reentrancy here. So what would it need to do? It would need to have some balance probably, and it would need to call withdrawal. And then when the message sender is called, and the message sender in this case is the contract. So the contract is called because that's the best way, or the best practice way, to send it an ether amount. So when it's called, it will call into the fallback function of this contract. And then this contract would be able to once again enter into withdraw, or maybe other functions of this contract. And this is dangerous, not because this is generally possible. This is only dangerous because of the order that the things in this function are happening. Because the order that things should be happening in is checks, effects, interactions. But what is actually happening here is that we do the effects last and the interactions first. So first it is interacting with another contract, and only then the effect that the balance is subtracted is applied. And that's problematic because now when the malicious contract takes over execution, the balance actually hasn't been updated yet. And that's a bad practice. We should follow the checks, effects, and action pattern and switch these two around. But even in this specific case, even if it didn't have a non-reentrant, and even if this would be possible, it wouldn't be really able to exploit anything, because when it finally returns and it comes back, and then it went here, then it made the call, but then after it made that call, it will continue here. So this balance subtraction would still be executed for every single call that was made. For every single reentrancy, it would subtract that amount. So the effect would actually be nothing. It would be no problem, even though it is actually a reentrancy. It cannot be attacked. It cannot be exploited. So there's no problem here. But as we said, non-reentrant, we are to assume that it works and that it is always applied. So even without it, it wouldn't have an effect, but with it, it especially doesn't have an effect because it's not working. And the way that this non-reentrant modifier prevents re-entering this contract is by having a state variable. Let's take a boolean, and call it entered. And by default, entered is false. So if this contract calls into withdraw, then non-reentrant is executed. And what does non-reentrant do? It sets entered to true. And while entered is true, or well, after setting it to true, it then executes the function body where the call happens, and only then the malicious contract can take over execution and try to enter again. But now what the non-reentrant modifier does every time is that it also, before setting enter to true, it requires entered to be false. So only if entered is false, it will set entered to true. And if entered is true, it will revert and not let this fallback call into withdraw again, or into any other function if the same modifier is applied to everything. And then when it continues, after executing the function body, entered will be reset to false. I should really practice writing. It will be reset to false again. And then, after successfully executing withdraw completely, entered has been reset to false, and then we can again enter withdraw. But now, when we can enter it, all of withdraw has already been run, so even if within this function things have been done in the wrong order, it doesn't matter because the whole function has already been executed, so the order is no longer relevant. But as we said, reentrancy is not the issue here. So let's go to B. Integer underflow leading to wrapping. And this is Solidity version 0.7, and 0.7 compared to 0.8 does not have the native protection against underflows yet, which 0.8 has. That means that if the amount is larger than balances, it will wrap. And what I mean with wrap is, for example, if you have a uint 8, a uint 8 has a range from 0 to 255. If you subtract 1 from 0, it will wrap around and go to 255. And that's a little bit problematic, because now we had a balance of 0, we subtracted from the balance of 0, and suddenly our balance is larger than it was before. So we don't even need any reentrancy magic to exploit this. We can just specify the amount, the entire amount that contract test has, all of the ether that contract test has, and send it to ourselves. And then it just makes the subtraction, and we will be negative, and it will just go through, and we will have been able to drain all of the ether from this account. That's kind of bad. So integer underflow leading to wrapping is definitely an issue here. Now, C is about the missing check on user balance in withdraw. And yes, if we had a check here, which basically just is a require that the balance is larger or equal to the amount, then we wouldn't have had to worry about any underflows here, because it wouldn't even reach any of this code basically. So a check is definitely missing. Alternatively to this check, to this explicit check, we could have used a library called SafeMath, which you can use to make subtractions with instead, which would revert if the subtraction would underflow, or if we were using the Solidity version 0.8, then it would if it would underflow, it will revert by default. In 0.8, it's basically the other way around. in order to make it not revert when it underflows, you have to add some special stuff. And what I mean by that is the unchecked block. And we would do the subtraction here, where we subtract the balance, the amount from the balance. So you can still have underflows in 0.8, but they would need to be in the unchecked block. The typical reason to use unchecked block is probably because you already have a check here, so you don't really worry about it underflowing and you're pretty sure that it won't happen. But in general, unless you're very sure, you should probably just not use unchecked block. But often, as gas is very expensive, people want to save gas, and so they start using the unchecked block, and that's where problems can happen when you use the unchecked block too much because you want to use to save more gas than you should. Well, anyway, so it cannot be all of the above.